Am I audible at the last? Okay. Today I'm going to talk about compositional reasoning and inference for weakly isolated transactions. And this is a joint work with my collaborators at Purdue. Right, a real-world application is almost always a concurrent program. So there are multiple clients that are being served by the application. Each client spawns a new thread of execution, and often the database state is shared between multiple threads of execution. And when the database is a shared state, transactions are the primary means of concurrency control. And we are often, it's very well known that transactions are governed by the correctness principles that are commonly known as ACID: atomicity, consistency, isolation, and durability. But this consistency is most often an application-specific property, and durability a low-level store-specific property. So we're going to ignore them today. I'm going to focus on atomicity and isolation. Atomicity is often called all-or-none property, allows transactions to commit in its entirety or doesn't commit at all. And isolation guarantees that a transaction cannot detect the presence of a concurrent transaction during its execution. Since transactions are atomic, it means that no other transaction can commit while a transaction executes, which guarantees the total order of transactions and serializability. So ACID semantics, in fact, guarantees strong or serializable isolation. On the other end of spectrum is the absence of serializable isolation, which is often called weak isolation, where a transaction can in fact detect the presence of concurrent transactions. Now this can lead to certain unexpected behaviors when serializability is assumed characteristic. So for example, we took a reference implementation of TPCC, which is a standard online transaction processing benchmark, and ran it with multiple concurrent clients on a stock Postgres database. And we found that in almost every run, at least one of the invariants are violated, and in total, 9 of 12 the TPCC invariants are violated in the experimental runs. So this happens because TPCC, like any other database application, is written assuming ACID model of database and serializable isolation. And Postgres, but for practical considerations for performance and scalability, defaults to weak isolation. And weak isolation does admit behaviors that are not possible under serializability, leading to violation of invariants in the case of TPCC. Now, this is not an isolated example. It so happens that databases in reality are rarely ACID. So there is a 2013 study which studied 18 popular relational databases and found that 9 of these 18 do not offer serializability at all. Of the remaining 9, 6 offer it as an option, and only 3 databases have serializability as the default option. So taken together, this means that real-world transactions are almost always weakly isolated, and strong isolation is more or less assured. And this can lead to unexpected behaviors, as we have seen in the case of TPCC. There's a recent studies published in SIGMOD which studied real-world applications, and they found that 2 million or 50% of all e-commerce applications are at the risk of being compromised because of isolation bugs. And these include big names such as Coca-Cola and Keurig and so on. Weak isolation, in summary, it improves performance by eschewing the need for synchronization, but it does jeopardize safety. So the rational thing to do would be to strike a balance, to basically use weak isolation when we are sure about safety and default to serializability otherwise. But this is not so easy, considering that the state space of isolation configurations is pretty large. For example, in the case of TPCC, there are 243 different configurations of isolation levels for transactions, and it is difficult to find out which among these configurations is optimal at the same time it's also safe. So what we need is a way to reason about transactions, individual transactions, in the context of safety of these transactions in the context of weak isolation. So that is, we need an oracle for weak isolation. But this is not so simple, considering that weak isolation understanding weak isolation is a serious problem. In particular, there are various levels of weak isolation that are implemented in real databases, such as read committed and repeatable read and so on. And these isolation levels, so to speak, are always defined with the low-level specifications, some in terms of database internal details, some in terms of anomalies, and the most formal among these in terms of constraints or program traces, such as happens before, visibility, and so on. So the difficulty with reasoning with these low-level specifications is that they are far removed from program semantics, and it's very difficult to bridge the gap between the high-level program semantics and the low-level specifications. There are also various implementations of the same specification, which often do not agree with each other. So in taken together, it's basically hard about reasoning about isolation on real databases. So this is the problem we try to address in the paper. So we basically propose a unifying formalism to specify weak isolation properties that is closer to high-level program semantics rather than low-level system-specific implementations. We also propose a reasoning framework for program safety under weak isolation that takes into account isolation-specific characteristics. That is, it makes proofs easier if the isolation is stronger, but requires programmer to reason about more interleavings if the isolation level is lower. And since in order to apply the scale verification to real-world programs, we have an automated verification tool that has a new take on how we should apply automation to these sort of programs. So firstly, I'll focus on how we specify weak isolation. So consider a database system with multiple transactions, TI, TJ, and so on, that are interacting via shared state. So the transactions witness the effects of other transactions through the shared state. Here represented using a triangle, I'll call it as delta. So TI witnesses the effects of TJ through delta. So let's say if TI witnesses a state delta at some time and a different state at a time Tn. So difference between both the states basically incorporates the effects of concurrent transactions. So to the first approximation, we can say that the isolation specification of TI specifies how the state that it witnesses at time Tn relates to a state it witnesses at time Tn during its lifetime. But time is an artificial artifact, so we define it in terms of an evaluation sequence of the transaction Ti. So we define the timeline or the lifetime of Ti, transaction Ti, as its evaluation sequence, and various times the points such as Tm and Tn as such as some prefixes of this evaluation sequence. So the evaluation sequence of Ti is shown in red on the slide. So while the transaction Ti progresses, the concurrent transactions also take effect. They commit and thereby changing the database global state. So we taken together, they're referred to as environmental transitions. So during the lifetime of Ti, it witnesses various states such as delta 0 and delta 1 and so on, each bearing effects of the concurrent transactions. Atomicity dictates that a transaction cannot flush its writes to the global state until it commits. So it is required to maintain a transaction local state. I call it a small delta. This is not an artificial artifact. In fact, it models something which is very real, it's called commit log. So transactions often keep commit log, and they flush the commit log to the global database state when they commit. So when the transaction commit, it flushes the local state to database state to actually have the commit step. Now, among the execution steps of the transaction, we can divide the lifetime into two parts. So the first, the execution sequence, and then the commit step. During the execution sequence, it basically leaves the database state unchanged while it changes the local state, and the commit step is actually where the global state gets changed. So we can basically incorporate these the execution time steps as stutter steps in the timeline of the system itself, and which basically do not change the global state, but commit step as the state that actually changes the global state. Giving us a linear evaluation sequence. So among these, now it basically suffices to specify, in order to specify the isolation level of Ti, the transaction Ti, it suffices to specify how delta changes between consecutive red transitions. Here, red representing the transaction Ti. So if a state delta changes between two consecutive red transitions, it means that it does incorporate certain effects from a concurrent transaction. Now, let's say delta and delta prime denote certain global states between two consecutive transitions of the transaction Ti, the red transitions. We can model the isolation specification of this transaction as a binary relation that relates this delta to delta prime. So, for example, the most trivial isolation specification being true, which allows any interference, that is, delta prime is in no way related to delta, so it can admit any interference between any two red transitions, which is more or less same as what's shown on the slide. The other end of the spectrum is where we require delta prime to be equal to delta, where no interference is allowed between any two states of consecutive transitions of this transaction. Now, this simple model is more or less sufficient. Between these two extremes is basically where we can specify various levels of isolation, which also include non-trivial isolation levels found in the database. So let's consider an example. Let's consider multi-version concurrency control, which is a common concurrency control mechanism used in databases such as Postgres. So what multi-version concurrency control does is basically it creates a snapshot of a database and executes a transaction against the static snapshot. So in this case, the transaction T4, which is shown in red, it is basically executed against static snapshot delta 0, while that state, while the concurrent transactions do make changes to delta 0. So the transaction nonetheless witnesses the only state delta 0, but it might commit to a different state that does incorporate the effects of concurrent transactions. Here in this case, for example, it commits to delta 3, changing it to delta 4. So we can distinguish between the two, the lifetime of the transaction T4 can be split into two phases, the execution phase, which includes the step AB, and the commit phase. So since AB see the same delta, we can think of it as being not admitting any interference during its execution. And then since, and the commit step commits to a different state, so we can think of aggregating all the interference into a single, during the single time phase between execution and the commit point. So isolation during the execution is delta prime equal to delta, which basically does not admit any interference. But isolation during the commit time is true, which admits all isolation, all the interference during the commit phase. So this lets us model basically what multi-version concurrency control does without actually referring to how it is implemented on Postgres or MySQL or such databases. So in fact, what MVCC offers is called repeatable read isolation. It's called repeatable read because if you repeat a read, you basically end up getting the same value during the execution, since the interference is only felt after the execution is done but before the commit. Likewise, other isolation levels can be, such as snapshot isolation, can be specified in a model, but with small extensions, just taking into account the components of the local state small delta and so on. So the second component is the proof system, which we need to relate isolation specification to the actual program semantics to facilitate rigorous proof of correctness. So what we need is a way to rigorously reason about concurrent program in composition with isolation. But recall that concurrent program can be reasoned about as a combination of sequential program and interference. So that's what relay guarantee teaches us, right? So substituting, we know that the concurrent program and isolation can be reasoned about as a composition of sequential program taken together with interference and isolation. So I group interference and isolation together. Let's call it interference modulo isolation. So as a result, we can reason about the combination as the combination of sequential program and interference modulo isolation. Interference modulo isolation is simply interference constrained by certain isolation characteristic. So it is still an interference, which means we can still use a relay guarantee style technique reasoning to reason about the composition. So the proof system in fact adapts a relay guarantee to transactions and weak isolation. And more formally, it lets us, it basically extends the relay guarantee reasoning with one component, which is the isolation specification. So I here denotes the isolation specification. And this in fact involves two major steps. The first is generalizing the assertions from unary predicates to binary relations that let us reason about the relation between the transaction local states and the global states. That is to track the internal changes of a transaction with respect to the what's happening to the global state. And the second generalization is basically generalizing the relay relation to a relay modulo isolation relation that takes into account the isolation characteristic. So it basically recall that the relay relation in a standard relay guarantee models interference step. So relay modulo isolation allows an interference only if the isolation specification allows it. So this now we can prove the stability of pre and post conditions of transactions with respect to relay modulo isolation, letting us prove stability only when it is actually needed, only when isolation allows a certain interference to go through. So these two generalizations, namely generalizing the predicates to binary relations and relay relation to relay modulo isolation, are the main generalizations done to, in fact, adapt relay guarantee to transactions and weak isolation. Now, the third part is how do we automate this reasoning? How do we automate this process of reasoning about transactions in the presence of weak isolation? Now, one conventional way is to think of these weakly isolated transactions as a typical shared memory concurrent programs. That is, they make changes to shared state, which is a database, and we reason about these changes in the same way as we do with an imperative concurrent program. But this involves a lot of artifacts such as global invariants, pre and post conditions, stable loop invariants, intermediate assertions, and guarantee annotations, and so on. So in general, the conventional wisdom tells us that these are hard to infer or annotate. So it may not be really productive to think of a concurrent database program, basically a set of concurrent transactions, as a typical shared memory concurrent program. But thankfully, we don't have to, because a SQL program, in fact, doesn't involve pointers, aliasing, or heap objects. And SQL programs are essentially declarative. So if you think of a SQL program, so it's composed of various well-defined interfaces to database such as select or update and so on. And these are tagged with high-level logical descriptions of what it does to database state. So in fact, we have a declarative characterization already present in a database program. And also, while the general recursion may be useful, the most often the kind of recursion found in database programs is control, in the sense that they are used to define certain recursion pattern over the set of tuples read from the database. So we can abstract out these recursion patterns into higher order combinators, and think of SQL program not as a sequence as a concurrent shared memory program, but as a monadic functional program, which operates on database as an abstract state. So basically, it abstracts of the database state as a set of records, and each basically database computation is basically a function that maps one set of records to other set of records. As I mentioned, iteration can be captured using higher order combinators such as map, fold, and so on, and also bind, because set is in fact a monad. In fact, bind plays is a major role in the semantics, as we'll see shortly. So here, for example, we go into detail. So we consider database as a set of records x, y, and z, and so on, and database computation that maps delta to a different state delta prime. So it can be thought of a function that iterates over these sets of records, producing new set of records for every set of record present in the original database. So and then unioning these set of records. So we can define the state, the semantics of the database computation in terms of the set and bind. So we call it state transformer semantics. So for example, let's say we have an update operation that updates a record y to y prime. We can iterate over the set of tuples, only update, basically mapping each tuple to a singleton set containing the same tuple, except mapping y to y prime, and then unioning the set of records. Likewise, with delete, we map the tuples to the tuple being deleted to an empty set. So this basically tells us that we can, in fact, use monadic set semantics to model the semantics of database programs. Now, this is not just a fancy way of representing database programs. It indeed helps us in automated verification, because we can map the database programs to a small, well-defined logical language that consists of sets and set monads and bind operation and union and other functions, which we call as monadic set language. So the advantage of monadic set language is that we can translate the monadic set language to a decidable fragment of first order logic, which can be analyzed using solvers such as Z3. So we have in fact implemented this approach of reasoning about database programs as in terms of set monad. We basically take we call the tool as ascertifier. So ascertifier takes a database program written as OCaml tagged with the guarantees for each transaction and the isolation specification for each transaction. It uses OCaml frontend to get the abstract representation of the program, and then uses basically it traverses the program to generate verification conditions in monadic set language. So it basically translates the program into monadic set language and generates verification conditions in this language. So we use that semantics preserving translation to translate monadic set MSL VCs into first order logic VCs, and we use Z3 to decide the validity of these queries. So this is what we call as a verification mode. Alternatively, we can issue this isolation specification and have a machine specification in terms of various isolation levels that it offers. So think of Postgres or any database as offering a lattice of isolation levels. We can iterate over this lattice to find out the appropriate isolation, the weakest isolation level for each transaction that lets us prove the program safety. So if we fail, we tie the loop back and go and iterate to the next level of isolation and so on. So this is what we call as inference mode. So we have in fact used this ascertifier to reason about the correctness of a few benchmarks, and that include database benchmarks such as TPCC. And because of most often the verification conditions are mostly in EPR, it's basically a decidable fragment of first order logic, letting us to get down the verification time below 1 minute for all the transactions in TPCC put together. In summary, database transactions in the wild are almost always weakly isolated. So we tend to think of, we in the PL community tend to think of serializability as the means of reasoning about database transactions, but that doesn't hold, that's not really the case in the wild. So conventional PL techniques focus solely on serializability, but we observe that weak isolation can be put on the same formal footing as serializability. It is also amenable to formal reasoning. And verification under weak isolation can be automated by basically modeling the database programs as monadic functional programs, which would lead to a tractable and, for the most part, decidable verification. Thank you so much.
Questions?
Hello.
So in this verification, right, you're verifying each transaction in isolation, the code of the transaction in isolation.
Could you come closer to
Oh, is this not working? Hello? Hello? There we go. Sorry. So when you're doing the verification, oh, you have to be very close. When you're doing the verification, you're verifying the code of each transaction in isolation, doing the rely guarantee, right?
Right.
Okay. So I'm just curious, in the semantics, though, that you showed at the beginning, right, you're showing a sequence of transactions actually executing, and now you're taking one of those transactions, TI, and you're saying, I'm going to split it up. But semantically, that means you've got to be doing that for every transaction, right? So for each transaction in the execution, each one of them is split up with respect to the other transactions.
Right.
So in the if you look at that semantically, then, is it a fixed order of transactions that each transaction is compared against? Is that how it works out, or are they allowed to pick their own orders?
No, the ordering is not restricted. It's basically it can be any order. For the example basically shows one linear order, but it can be any order. So relations can be considered in any order.
So, but given a execution, I have T1, T2, T3. So if I'm verifying these, do I verify each of them with respect to the same order, or could each transaction see a different order of the others?
So the order does not matter, because a relay abstracts away basically what concurrent transactions do as a relation between two states. So it basically doesn't need to take into account the order in which the transactions actually execute.
Okay.
More questions? Can you go to the previous slide, to the figure? Yeah, I probably missed something. Where's the rely condition? Are you assuming the rely is the same with guarantee? Where's the rely condition?
So it's basically, we have guarantees for every transaction, and so when we are verifying a transaction, the rely relation is computed as a union of guarantees of all the transactions in the system. So it lets us verify.
Okay. More questions? Okay, then let's thank our speaker.